Okay, so this is just sort of the geometry of how a gradient descent algorithm would proceed. Okay, you would have this zigzag behavior and orthogonal self. Now, yes, question. Yeah, correct. This proof is not telling us. This proof in fact requires me to take 2 steps. Only then I can talk about orthogonality. But what we are saying is that there are some special directions where I just reach in one shot. That is not covered in this only. But we will prove that later. We will figure out when does it happen. Can I say anything about it? Okay. No, this is in general. What we are saying is that if the contours are circular, I will reach in one shot. If the contours are anything but circular, I will go in a zigzag way, with the property that every subsequent step is at 90 degrees.
Like the starting point and the gradient at that point is in such a way that for some alpha we reach the minima, then we'll reach in one shot.
Yeah, if it so happens, if all the stars align that the gradient.
It can be circular, right? It can be some contour, but the starting point should satisfy this.
No, it will actually have to be circular, because at each point you are, you should not, the function value should not increase. Your algorithm will end there. So if you have a circular contour on the outside and some funny contour inside, then if you're going along that line, it is possible. I can construct some kind of a landscape where at some point you will begin a ascent.
Like, the contours being circular is a sufficient condition, but is it necessary?
In this case, yes. And again, as I said, we'll come to it. And we'll come to it when we do the next thing which we are going to do. We have spoken about descent directions. We have spoken about Wolf conditions, what are the conditions that the step length should satisfy. But so to speak, the elephant in the room, no one has asked the question, is there any guarantee that gradient descent converges? Does there exist a solution? We are just hoping that and praying that a solution exists, but people would like to know, does a solution exist? Can you prove it to me that this algorithm will converge, right? So this is really important. 2 questions, convergence and the convergence is kind of, does it converge, yes or no? If it converges, that means it exists. The second is rate. At what rate do I converge? So the good news is that yes, there is convergence, right? In the sense that wherever I start, let us write that down. I reach a stationary point. In other words, wherever I start, I will reach the nearest local minima. So this is not a proof that it will reach the global minima, right? So this is saying that wherever, whichever, so to speak, whichever valley I start in, I will reach the bottom of that valley. Whether or not that valley is good enough for you is, your call. Okay. So I am going to go about the proof of this now, so that we get, particularly for this algorithm, I am going to do the proof, because this algorithm, the steepest descent or the gradient descent algorithm, is used so extensively in AI/ML, which is why I think it's important that you know the proof, how does it go through, and there are like 10,000 variants of this proof, depending on the latest algorithm, Adam or this, that and the other, which people use to calculate the step length and all of that. The skeleton of this proof is used by all other guys, so we'll prove this over here. Okay. So let's write down a few things that we will need. One thing is the angle. Remember, we spoke about, when we spoke about the whether or not a direction is a descent direction, we spoke about the angle between pk and the negative gradient. That angle should always be in a cone of 90 degrees, right? So to quantify that a little bit better, I am going to define this angle, right? So I am going to define theta k. How will I define it? Simply by an inner product. So what will be, for example, cosine of theta k equal to? Right, we just use the definition of inner product. What is inner product of, if I say A transpose B, what is it equal to? Norm A, norm B, cosine That's the same thing I'm going to use here. And what are the two characters I'm interested in? The descent direction pk and the negative gradient. So this is going to be minus grad fk transpose pk, and since it's cosine I need to normalize it. Okay. Obviously theta k equal to 0 corresponds to what? If I were to choose theta k equal to 0, I am picking which pk? The negative gradient, right? So this is steepest descent. Okay, but in general I can have minus 90 theta k 90. Okay, and when this is the case, can I put down any inequality for cos theta k? If the angle is always between minus 90 and 90, what value does cos take? It's always positive, right? So this is fairly simple trigonometry that we need to keep in mind. Okay, so this is just some definition that we will use. We haven't started the theorem yet. Okay, so let's note this down. Okay, so now point B is actually point B. I'm going to state the theorem. Okay, and then we will sort of get some intuition and then try to prove it. It's a difficult spelling also to write this person's name. I don't know which country, probably Dutch. Zoutendijk's condition is called. Remember, we are doing line search implies we are doing something like this. Right. So what are we assuming? We are going to assume that this is a descent direction. This is the first thing that we are assuming. We need to assume something about alpha k. What is the most reasonable thing that you would say alpha should satisfy? Based on what you know so far. Supposing you were in charge of this algorithm, you won't be okay with some random alpha, right? You would want alpha to satisfy something. What is that something? That is exact line search. That is too strict. Something lesser than that? We've studied it. Wolf conditions, right? Wolf conditions is sufficient decrease and the curvature condition, right? So satisfies. With these two ingredients in place, I am all set for doing gradient descent, right? Insisting on exact line search may be too strict. Okay. So what are the conditions of the theorem? They are all very, what should I say, reasonable conditions. The first condition is the function should be bounded from below. I call this the idiot check. Why should we call this the idiot check? Supposing I say find me the minima of 1 by mod x. It doesn't exist, right? I mean, minus infinity is not a number, or in whatever, right? So the function has to be bounded from below. Only then does it even make sense for you to do optimization, right? So this is very much common sense. The next two conditions are basically to ensure I can do calculus. So they are going to be about continuity and differentiability, right? So we'll just note that down. F is continuously differentiable. And the second is that the gradient of f, the gradient of f is Lipschitz continuous. Okay. We've all had a review of Lipschitz continuity simply, and I am saying that the gradient should be Lipschitz continuous, right. That means if I take grad of fx minus grad of fy, what should this be? Less than equal to L times norm of x minus y for all x and y in the some open neighborhood. Okay. So, this is what I need, these are the conditions of the theorem, right. Now, if all of these conditions are satisfied, now I will write down what is the Zoutendijk's condition, right. So, this is, you can think of this as the if part and then I have the then part. Okay. Then looks a little grungy. Does not look like what you were expecting. It is saying that if these fairly straightforward conditions hold true, then this big summation is what is not blowing up, basically that is what it is saying. It is less than infinity means it is a bounded number, okay. K is left to us, that means K can be as large as I want. So, it is saying that take K to be whatever you want, as large as you want, this summation somehow is always going to be less than infinity, means it is a number, it is a finite number, right. So, from here, before we sketch out the proof, can you kind of guess how does this imply that gradient descent converges? Just intuitively, because it is better to get an intuition before we go into the grungy details. Let us assume that you know the proof and now you have this statement in front of you, this summation is less than infinity, what can we say? That means it is the summation, I keep adding terms, are each of the terms positive? Cos squared is positive, norm squared is positive. I keep adding positive terms, keep adding, yet this number does not blow up. What does it tell you about what I am adding in? It must get smaller and smaller and smaller, right. If it gets smaller and smaller and smaller, what is as small a positive number can get to? 0. If it is 0, what is that final term which I am adding? It is cos squared theta j, or in this case it will be cos squared theta k and norm of fk squared, right. If it is a descent direction, can cosine theta be 0? No, right. A descent direction means it should be within the cone of 90 degrees. If I choose it exactly 90 degrees, then I am actually walking along the contour, I am not doing any descent. So, exactly 90 will not be permissible. That means it is some positive number, however small you want to take it. What is left? Norm of grad fk equal to 0 or tending to 0. What was our signature of a stationary point? That the gradient is 0, right. So, you see that this what looks like a ugly summation actually is concealing one very simple truth, that in the limit as k becomes very large, the gradient goes to 0. Gradient goes to 0 means this is a stationary point. So, when you appreciate this, then the proof becomes easy to follow. Is the intuition clear to everyone? Okay. Yes. This is what Zoutendijk derived. You want to put extra limits on top of this, it is up to us, which is what we kind of did. But this, when you know, what did this person, what theorem did this guy prove? This is what he proved. So, we have to be true to what he did and then we can draw corollaries from that. Does the k have to be bounded? Well, we are just taking k to be, I mean, we are taking k in the limit, I mean, as a large number, but I mean, the k, yes, k does represent the number of iterations. So, what it is saying that as I add, no matter how many I add, this summation is staying finite. So, therefore, at large number of k, and how large a k will depend on the problem, this is going to go to 0, right. Contrast this with the case where you do not have any such guarantee. You may have an algorithm where norm of grad fk, there is no proof that it becomes smaller and smaller, That's the case where you are really, you have no clue whether this is ever going to work. This is telling you, if you wait long enough, it will work. Now, how fast it will work and all will be covered in the, when we talk about the rate. Okay, this is telling us that it will converge. That's the good news.